All right, this is Kinetics lecture part 3. I wanted to mention that on the rate law, you can see here that the coefficients are 2 for A here and 1 for B here. But when we look at the rate law, the exponent term is 1 here for A and 0 for B. So M and N don't appear to be connected to this. We wouldn't put 2 here and 1 here like we would in the K expression, equilibrium constant. So it's different than the equilibrium constant. You have to keep that in mind. Now, coming down here, we were asking the question, how much time and what is the concentration? So we're interested in changes in concentration and changes in time. For zero order, it's fairly straightforward because what we have here is this. We have that the rate is equal to delta concentration over delta T, and this is just equal to a constant, the slope. Actually, it's negative the slope because we want this to be absolute value here. The slope is going to be negative here if this is a reactant, like for example A or some reactant. And that we're just going to call K, the slope for that. Now, what this means is that we can come up with equations for this. So, for example, what we can do is we could just solve this for delta A here. I'm just using A for some reactant concentration. This is going to equal minus K times delta T. And delta A, what that's going to give us is it's going to give us A at time T minus A at time initial. And this is going to equal minus K. Delta T is going to be T at time T minus T at time initial. So in other words, it's final minus initial. Maybe I should use that instead. There, minus initial. Might make it a bit better. All right. Now, what we can do is we can let T initial be 0. So if we start at time 0, so if T initial is equal to T0, which is equal to 0, seconds, minutes, whatever, etc., then we can simplify this equation. This is going to be A at time final and minus A at time 0, so that's our initial, is equal to minus K T final minus T initial. T initial is just going to be 0. We're starting the clock at 0. And so this is going to simplify into this. A at time final, or A at time T, is equal to minus KT at final plus A at time 0. Alright, so if we're interested in how long something takes, this is going to be how long, the delta T is how long, and the delta A is how much. So if we have questions about how long and how much, then this is the equation we'd use. We could calculate the concentration of A at any time, interval from 0 to whatever time final we have, as long as we know what A initial is, and then, or we could calculate the time it takes. T final would be the time, and so we could just simplify this here to just T. We'll just call that T, or just T. So, this is what is termed the integrated rate law, and the integrated rate law, we could figure this out from calculus. The origin of the integrated rate law here from calculus. And so what we do here is we have d A, when we have this small delta over dt is equal to minus kt. And what you do is you do something called integration of this, and then that leads to this equation. But we just solved for it algebraically. We didn't have to use any calculus to come up with this equation. However, when the slope is changing, we do have to use some calculus to do this. When we have to use some calculus, then what we're going to do is we're going to simplify things. So when we have a question like how much time, what is the concentration at a given time, what we're going to do for all of these, we're going to restrict it to this type of reaction. That is, AA goes to product. So there's only one reactant, so we call this like a decomposition type reaction. There's only one reactant that decomposes into products. So for example, hydrogen peroxide is one reactant that decomposes into products, two products, water and O2. But here, the reason that we do it is to keep the math. We're just doing what we call single variable versus multivariable. We're not going to, multivariable is beyond the scope of this, so we're not going to get into the mathematics of that. So we're going to focus on single variable only. Multivariable is beyond 1b. And so the first thing is we're going to restrict the type of reaction. So the next example is, the first example is going to be zero order. This will be a zero order equation where the rate is just equal to this, the rate law. And so zero order actually comes from this. Rate law. The rate is equal to minus k times a to the zeroth here. And then what we're seeing is that no matter how the concentration of A changes, I'm at a truck stop, so that's what, if you can hear the intercom there. But anyways, it's how the concentration of A changes. As it changes, it has no impact on the rate, and therefore we just see it decay linearly. And so this is that linear decay that we were talking about earlier. It's just a straight line decay. It's the concentration of A versus time. It does not change. For the hydrogen peroxide, it was not a linear decay. For the hydrogen peroxide, we saw a curve like this. In fact, if you do the concentration of hydrogen peroxide here, we can see that when half of this decomposes, it takes this long. It's T1 half. And the next half-life is the same length. And so we have this constant half-life decay like this. And so we already saw some of the patterns there. And these patterns we can generate mathematically as well using calculus. And so what we do is we take the rate. So this turns out to be a first order decay because of that. I mean, we could also measure the slopes of the tangent lines, and we see that the slopes, each time we cut the concentration in half, the rate gets cut in half as well. And so this is first order based on the shape of the curve here. Now, the rate law for this is the rate is equal to I made an error here. This is not minus k. Sorry, it's just k. I need to correct something. This is where k is the negative of the slope. So if we measure the slope here, the slope is negative, and so that's going to equal negative k, and so k is equal to negative the slope. That's what I meant. for that particular equation. So sorry, correct that. It's a negative of the slope here, which is the k value. And so that makes it positive. The rates all need to be positive. Now, here, the rate is equal to k. And now, first order, the way it's going to work is, okay, we're going to call this A, like hydrogen peroxide will be A. So this will be AA goes to product. In this case, we have one hydrogen peroxide going to product. So we put hydrogen peroxide here, but I'm just going to use the generic reactant A, and this is going to be first order. So if the concentration of A gets cut in half, then that's going to half the rate. If the concentration of A gets cut by a quarter, it's going to quarter the rate. And so this is it. But, the problem with this is we have our delta A over delta T. But this is constantly changing. So as the reaction progresses, sorry, it's a bit noisy in here, but it's constantly changing, and so that makes it difficult. And this is why we need calculus. And so it requires calculus. But calculus is not required for this course. So what we're going to do is we're just going to use the equations that are generated from calculus. And so if we do this integration stuff, so we integrate, this is a symbol for our integration. Whenever we integrate this, we come up with an integrated rate law. And we have one equation which we can have in rearrange into different forms. So the two common forms for this equation are this. Now I'm going to call T0 0. Okay, so we'll let T0 equals 0. If it's not, then we have to put a delta T in here instead of a T final. So what we're going to get is we're going to ln of concentration of A at final over A initial, which would be 0, is equal to minus KT here. Oh, did I get that? Yeah. And so that is going to give us, this is the correct equation here though. It's KT. Yeah, anyway. Okay, going down here, so we have this is equal to minus KT, or another way of expressing this is we can go like this. ln of the concentration of A final here is equal to minus KT plus ln A initial. So this, we can make a linear plot. Y is equal to mx plus b. B is going to be a constant here because A0 is not a variable here. And so this equation here is useful for figuring out how long or how much over here. How long, how much. So that's it. And then what we can do is we can do this. We can make a plot. So if we were to plot ln of A versus t, then what we'll get is we'll get this linear line, the straight line. And so a plot of ln of A versus t is linear. A plot of A versus T is nonlinear. We saw that up here. This is just A, in that case, hydrogen peroxide. So these are equations. So this rate law tells us, how fast it is at various temperatures. And then we have the integrated rate laws, which are going to tell us how much, how long. And then we have this form of the integrated rate law, which you can get. Now, this form of the integrated rate law is interesting because M is the slope here. And so again, we see here, if I want to determine K, I can get it from the slope. And so K is equal to the negative slope here from this line. Okay. The last example would be for a second order. And so once again, we're going to restrict it to single variable, that is A goes to product. Yeah. And then we can get the rate law. The rate is equal to K A squared. This is going to equal delta A over delta T. And we have this thing. This is constantly changing. So we can't just use simple algebra to figure out what delta A is and delta T, because delta A changes depending on the time interval. It gets bigger or smaller. And the same thing with delta T. So since it's constantly changing, we have to use calculus to figure this out. And so again, we'll do this thing, this integration, and that's going to lead to the integrated rate laws. The integrated rate laws for this primarily use just one form for the integrated rate law here. And the integrated rate law is going to look like this after some rearrangement. It's going to be 1 over A at time t final, or final, is equal to plus kt plus 1 over A at time 0. And so a plot of this is going to yield something like this. It's again going to be linear. So if we plot 1 over A versus T, we get a linear plot. And when we look at the line here, this is y is equal to mx plus b. And so the slope here is going to equal k. So this is already positive, so we don't have to change the sign. So the slope is equal to k. Again, rate constants and rates are positive. And so, okay, we have that. Now, one of the things we could do with these equations is let's put it to use right now. So an example of using the integrated rate laws. We can determine T1 half for the various orders, T1 half determination. And so one of the T1 half is going to be for 0 order. And so when we do T1 half, we're going to have at time 0, we'll have the initial concentration, we'll call it A0. And then at time T1 half, we're going to have 1/2 of A0 here. That's going to be it. And so for first order, we had this particular equation, which is A at time t is equal to minus kt plus A at time 0 here. And what we're going to do is we're going to substitute. So 1/2, this is going to equal minus k. We're going to say that this is T1 half, and therefore A times T will be 1/2 times A times 0. And this is going to be plus A times 0 on the end here. And so I'm going to subtract 1/2 A times 0 and add KT 1/2 both sides. So I'm going to KT 1/2 is equal to 1/2 A times 0. And then T1 half is equal to A at time 0 over 2 K. So this one is just your initial starting point. A times 0 is just your initial start point. Initial start point. In this case, it would probably be better to use A sub initial. And then T is just going to be the delta T from the previous. But if it's from the previous, then you wouldn't do it. So what I mean by this is this. Okay, if we look at the first half-life here, let's say it goes down here. So look at the first half-life, this T1 here. Now T1 half is going to be A times 0 over 2K. But what happens here is A times 0 now is 1/2 what it was before. And so the T1 half is going to be, well, this is going to be actually 1/4, which is going, or actually 1/2 the previous, which is going to be 1/4 original. So it's going to actually double in the time. As the concentration, those will go down to 1/2 concentration. And so the next half-life is going to be longer. And so what I mean by, this is your original 0 here, and then we cut it in half. Now this is your new 0 point, and we cut that in half. So if you do that, it's your start point, your initial start point, and this one's going to be twice as long when we do the math for this. Okay. Did I do the math right here? Let me make sure I did the math correctly. So it's going to be 2 halves, 1/2, yeah. Yes, this goes over the. Alright, this is for 0 order. We can do the same thing for first order. We'll do T1 half analysis. And so we're going to use this one, ln of A times T over A times 0. Your initial start point is equal to minus KT. Okay, then at T1 half, the A at time T is equal to 1/2 of the original A times 0, and T is equal to T1 half. So we'll substitute that in here, and we end up getting this ln of A times T, which is 1/2 A times 0 over A times 0. And A times 0 is cancelled. Is equal to minus KT 1/2. And then we can solve this. T1 half, we'll write that over here. T1 half is equal to ln 1/2 divided by K. And I guess we have a negative sign there. And this ln comes out to negative 0.693, and then this is going to be positive, so it's like 0.693 over K. K is a constant, so the half-life does not change. It remains the same. So we'll just for 0 order, the half-life did change because it depends on the concentration. So as the concentration of A is changing, so is the half-life. Here, there's no concentration of A. This is a constant, that's a constant. So the half-life is fixed. It's constant half-life. Then finally, we can take a look at analyzing second order for T1 half. So second just write it like this. The second order integrated rate law is 1 over 8 times t is equal to kt plus 1 over 8 times 0. So this has a positive slope, so we don't have to change the sign on that one. And so 8 times t again is going to equal 1/2 8 times 0. And then p is equal to t 1/2. And so we just plug that in here. We're going to get 1 over p, which will be 1/2 8 times 0, is equal to kt plus 1 over 8 times 0. So I'm going to invert and multiply this. So this is going to be 2 over 8 times 0. So this term changes to 2 over 8 times 0. So what I'm going to do is I'm going to subtract 1 over 8 times 0 from both sides. And this is going to equal kt 1/2. Maybe 1/2 here too. Alright, and so this is going to give us 2 over 8 times 0. And then we're going to divide that by k. So I'm going to both sides by k, and this is equal to t 1/2. So essentially, this is what happens in zero order. The half-life gets cut by 1/2 each successive time. So the half-life gets shorter and shorter. This is not. Let's take a look at these. This is not a zero order curve here. This is first order curve. This one belongs down here. This is first order. A zero order curve is a straight line. So what happens here is that we have our first half-life, our second half-life is going to be cut in half, 1/2 here. Let's see that, and so this is going to be shorter here. And the next half-life is going to be cut in half too. So these successive t1/2s are going to be half as long each successive time, and we end up with a linear plot like this. Not the greatest one. Over here, for first order, it's just a fixed t1/2, so we all get the same t1/2. Actually, this is not. This curve doesn't look first order. Sorry, this curve looks like it's a second order. I can tell because look at the half-life. The half-life is growing. Looks like it's growing. That's not first order. First order should have a constant half-life. So let's see what a first order would look like. And so, sorry, the second order. Oops. A first order is going to have a constant half-life. Come on. Okay. I'd like to finish this again. Okay. What we'll do then is to be continued. So we'll have a part 3 after this goes. I'm going to cut the video now. We'll do another one.